Welcome everyone. My name is Chris Friedemann and I'm the Chief Marketing Officer for NEOS GeoSolutions. Over the next roughly 15 minutes, I'm going to take you through a quick tour of how our multi-measurement methodology is used to support oil and gas exploration and development. NEOS is a company founded on delivering better surface and subsurface insights through the integration and interpretation of as many geoscience datasets as possible. These datasets include both conventional sources of information, such as seismic and well logs, and less conventional sources, such as measurements obtained from radiometric and hyperspectral sensors. While we do own and operate aircraft used in the acquisition of some of these less conventional datasets, our focus is on data integration and interpretation. This is consistent with our belief on where the value can be derived, and is also consistent with the legacies of some of our largest investors, including Microsoft's Bill Gates and Kleiner Perkins Caulfield and Byers, the venture capital firm that backed Google more than a decade ago. To date, most of our work has been done in the Americas, though we have recently opened an office in Dubai and are actively pursuing projects throughout the resource-rich Middle East. Our multi-measurement methodology finds application throughout the geologic column, from the basement to the surface. Over the next few slides, I'm going to take you through some example applications, starting first with the basement. As all geoscientists know, the basement is the foundation upon which all the other sedimentary layers rest, hence its name. As the foundation of the geologic column, understanding the basement is vital to understanding what is going on above it, including in the reservoir zones of interest. For example, oscillations in the topography of the basement can often expose source rock intervals to differential heat levels, which can affect the thermal maturity and hence liquids generating potential of source rock and shale zone intervals. In other cases, the basement might be intersected by lineaments and faults, which can often play a part in the deposition, thermal maturation, and fracture distribution in the shallower intervals. To give you an example of the utility of basement measurements, I thought I'd share this gravity-derived image from a portion of California's Ventura Basin. The areas in purple represent deep sedimentary depot centers within the basin, while the hot colors represent areas with less sedimentation. Producing wells are noted in black, while the blue dots represent dry holes. This image doesn't really provide a way of looking at the depth of these wells, whether producing or dry. But what our Ventura project underwriters are using this data for, in part, is to locate depot centers that are relatively underexplored compared to the surrounding areas. You'll note two areas of potential interest, including this area in the center of the image, and this valley-like feature opening up to the south. What's interesting is that these features weren't noted previously by major operators in this area, even though the Ventura Basin has been undergoing E&P activities for more than 150 years. Moving up in the geologic column, you'll note some of the applications of our methodology in the reservoir interval. Fault and fracture mapping is a key application for us in many regions, especially in North America, given the huge investments that are going into unconventional shale development. In some cases, our E&P clients want to target naturally occurring fracture swarms. In others, they want to avoid them and rely upon man-made hydraulic fractures. Fault and fracture systems can often be detected with a variety of non-seismic geophysical methods, including gravity, magnetic, radiometric, EM, and hyperspectral. Here, you're looking at an analysis of a single measurement, magnetic. The red color correlates to an anomaly of a magnetic derivative in the Manco Shale of Colorado's Piceance Basin, measured using a helicopter-based sensor. The areas noted in red appear anomalous for several reasons, but a key one is that groundwater preferentially migrates along fault and fracture systems, causing magnetite destructive alteration. In this particular part of the Piceance Basin, naturally occurring fractures are a good thing, as well productivity improves when fracture fairways are intersected. We were asked to help our client explain why some of their wells were more productive and others less so. The red inverted V pattern you see here corresponded to their most productive wells and was also noted on core data taken from several of them. With this insight, our client now has a better idea of where to target its next round of drilling in an area in which seismic data acquisition is both operationally challenging and high cost. Moving up to the near surface, we're helping our clients identify both geohazards that they are seeking to avoid, as well as indicators of what might be going on in the reservoir zones below, such as whether there might be faults or fracture networks that could have breached prospective reservoirs below, or signs of micro-seepage that may help to further de-risk the exploration potential of a deeper target. In this example, you're looking at two images from two different regions in North America. The image in the upper left is from Western Canada and depicts, in red, shallow gas-filled channel sands that were detected with an electromagnetic or EM sensor. In this area, they are a reservoir target. In the image to the lower right, you're looking at an early 3D representation from an area in the Appalachian Basin. In this case, gas has naturally migrated from the Marcellus and other intervals and become trapped in the first 1,000 meters of the near surface, most likely in the areas denoted by the hot colors, which represent a high resistive response detected with an EM sensor. Although some operators are attempting to commingle these shallow gas zones in Appalachia, for our primary underwriters of our Tioga County program, these shallow gas stringers represent a geohazard that they wish to avoid. I might also add that this type of image, taken early in the development life cycle of an E&P opportunity, can represent a bit of an insurance policy for an operator, as it lets them demonstrate the locations of naturally occurring gas intervals before E&P operations, including hydraulic fracturing, begin in earnest. Finally, we move to the surface where a series of measurements, most notably hyperspectral, but also magnetic and radiometric, serve to inform our multi-measurement methodology. For those who aren't familiar with hyperspectral imaging, I'd like to refer you to the resources page on our website, neosgeo.com, and the Hyperspectral 101 narrated slideshow that you'll find there. Hyperspectral is a pretty amazing technology. As we use it at NEOS, we analyze more than 600 channels across the visible and invisible light spectrum in 3 by 3 meter pixels on the surface of the Earth. Every substance reflects and absorbs energy from the sun, which serves as our primary source, in a unique way, effectively giving each of them a unique spectral fingerprint. We then compare these spectral fingerprints to our proprietary library of nearly 1,000 substances, which include both direct and indirect indicators of hydrocarbons and minerals. This allows us to identify oil seeps or gas plumes directly, along with the indirect effects seepage might have had, including the effects it might have had on vegetation, or the unique minerals and alteration zones such seepage might leave behind. If you think this stuff is pretty cutting edge, you're probably right. But it was good enough for the CIA and the NSA to use in planning the SEAL Team 6 raid on the hideout of Osama bin Laden in Pakistan, reportedly to determine the composition of the walls surrounding his compound and, by association, the nature of the explosive charges that would be needed to successfully breach them. Here's an example of hyperspectral in action, but in combination with other measurements. Looking at the image on the upper left, you'll note several pink blobs. These correspond to methane gas plumes on the surface. These could be associated with gas migrating up faults or around old abandoned wellheads, or with biological sources, such as mounds of animal waste. But it's an indicator of an anomaly of some sort. By comparing hyperspectral anomalies to other indicators, such as faults, as shown on the image on the lower right, or old abandoned wellheads, we have a chance of determining where the methane is coming from. With respect to the lower right chart, the faults were inferred based on an analysis of magnetic anomalies similar to what I referenced in the peons earlier. We can also compare the gas sources to our inferred zones of trapped gas in the near surface based on resistivity anomalies using the EM sensor, as I described a couple of charts back. We often get asked how many datasets we make use of in our multi-measurement projects, and where they all come from. This slide attempts to show some of the data and some of the sources we use. We start first with an evaluation of what's available in the public domain and for license, including USGS maps and GravMag datasets, 2D and 3D seismic libraries, and public satellite data like ASTER, which comes via NASA's Jet Propulsion Laboratory. We then acquire, on our own or via third-party vendors, some or all of the data sets you saw on the last few slides, depending on the project. We then combine all of these with existing data we might have in our data archives, for instance if we've done a project in the area before. And then we integrate these data sets with client data, including proprietary maps, earth models, well log and production histories, and any interpretations that our clients are willing to share. All of these data sets are brought together in a secure, web-based data management, integration, and interpretation platform that we continue to develop and which we call the NeoSphere. Some of the key multi-measurement data sets we utilize on our projects are shown here. Gravity is key for helping us understand deep, basement-related features, and more recently is serving as an input to some brittleness work we've been asked to undertake by a supermajor. As many of you know, shale brittleness can be critical to the success of hydraulic fracturing programs in an unconventional shale. Brittleness is itself influenced by a parameter called Young's modulus, which itself is strongly tied to density. Since gravity sensors essentially measure density variations, special analysis of the data can yield insights into brittleness. Magnetic measurements are especially valuable in fault and fracture system detection, but are also being used to help identify legacy infrastructure in areas undergoing new waves of development. EM data is especially helpful with near-surface geohazard detection, including the location of trapped shallow gas. Hyperspectral imaging provides a wide range of insights into substances on the Earth's surface, including direct and indirect hydrocarbon indicators. It also serves as a key input to environmental baselines, including defining the time-zero state of the health of vegetation and waterways. Lastly, radiometric sensors help us detect subtle fault and fracture systems and anomalies that might be associated with trace hydrocarbon leakage over time. We've also been asked to look into certain radiometric measurements as predictors of total organic carbon, or TOC, in shale zones in the subsurface. The measurements we've been talking about are acquired from a variety of airborne platforms, including satellites, fixed-wing aircraft, and helicopters, depending on the objectives of any particular project. Fixed-wing aircraft tend to be our most commonly used acquisition platform, and are a key part of our basin-scale imaging solution that we call a NeoBasin. These NeoBasin surveys generally cover a minimum of 1,000 square miles, though they can be much larger. Helicopter-based surveys, which we call NeoProspectors, cover a smaller area, generally 50 to 100 square miles. In all cases, the airborne nature of these acquisition methods let us cover large areas safely and efficiently without major permitting issues and without the need to put large teams of people on the ground. For example, compared to a seismic survey that could cost upwards of $100,000 per square mile, a NeoBasin might cost a few $1,000s per square mile. And the results can be delivered to our client in roughly 6 months, which many of them then use to better target their high-cost follow-on 3D seismic programs. In terms of what we do with the data once it's acquired, we roughly follow the 4-step workflow shown here. First, we process and interpret each of the measurements individually. So we'll analyze the spectral signatures of hyperspectral data, looking for hydrocarbon indicators, or interpret magnetic derivatives, looking for suggestions of faulting or fracturing. Then our interpreters, working in partnership with client personnel, will make qualitative interpretive judgments about what they're seeing. So, for example, they might be looking for alterations in deep basement topography and or evidence of deep basement faulting, and then see whether these features might be affecting the nature and density of fracture systems in the reservoir interval. Lastly, we run some quantitative analyses on the data, which can vary depending on the objectives of the project at hand. But these quantitative analyses might include the development of geostatistical probability models or the simultaneous inversion of several geodata sets. Generally, this entire workflow, from processing to quantitative interpretation of the data, takes about 4 months. So here is an example of one of our quantitative fusion products. We are looking at data from our Ventura NeoBasin survey, with the area in the black outline encompassing roughly 1,000 square miles. The colors shown correspond to our geostatistical assessment of the probability of finding liquid hydrocarbons in this particular geologic horizon, called the Pico, a dataset that is the shallowest we analyzed here in Ventura. Hot colors correspond to a greater probability of finding oil. The black dots are known producing fields. The way this is developed is we identify the series of geological and geophysical measurements that correlate with known fields, though we could also look for correlations with the highest producing wells in an unconventional shale reservoir, for example. We might look at more than 100 individual measurements and derivative products throughout the geologic column, but generally we'll find about 20 that correlate with the sweet spots that we're looking for. These measurements could be from anywhere within the geologic column, and among other things, might correlate to the distance from mapped faults and high spots in the basement, the intensity of fracture systems in the reservoir interval, and evidence of trace hydrocarbons in the near surface or surface. Once the correlations are established, our algorithms then hunt for similar anomalies elsewhere in the basin, with areas like these being of interest to the interpreter and worthy of further investigation. In the case of Ventura, the analysis becomes even more intriguing as we go deeper in the geologic column, as the number of well penetrations is less and the chances of finding untapped reservoirs even higher. I should point out that this sort of analysis is equally applicable in an unconventional shale basin as well. In this case, we'd normalize for the effects of completions, for instance, the number of frac stages, and look for the combination of measurements that correlate with the highest producing wells, in essence, the sweet spots in the shale. In this, our final slide, I wanted to give you a feel for where we have completed projects. As you can see, we've tended to focus on projects in the Americas, although we have just opened an office in Dubai and are partnering with one of our Saudi investors to launch our presence in the Middle East. Our biggest project is currently underway in Argentina's Neuquén Basin, where a supermajor has recently underwritten a major extension of our Neo-Basin program. We also have several projects underway in Appalachia, helping a supermajor and a couple of large independents optimize their exploration and development programs for the Marcellus and Utica shales. We have also worked on projects in California, with an initial focus on the Ventura Basin, but with planned expansions into the San Joaquin, Santa Maria, and LA Basin areas. Lastly, we're working to expand our footprint in the Rocky Mountain region, as we believe our methodology could be highly relevant in many of the complex, environmentally sensitive development areas of the Mountain West. Thanks very much for joining me today. If you'd like to download a copy of this presentation, please click on the attachments link shown in the upper right portion of your screen.